Thanks, Marco. Thank you, everybody, for joining us today for this webcast. My name is Omo Clement. I am RainDance's Global Product Manager for all next-generation sequencing products. This morning, we will be presenting on our new NGS Target and Enrichment Cancer Panel called ThunderBolts, specifically on how to maximize the ability to analyze challenging FFPE and plasma samples using this ThunderBolts Cancer Panel. Presenting this today is Jeff Olsen, who is RainDance's Director of Genomic Applications. Jeff has been with RainDance for about 6 years and currently runs the Genomic Applications Group. His group's main focus is in developing applications and assays that run on all RainDance technology platforms. Besides his scientific work, Jeff is an avid sports person and fan, and he's a member of the RainDance's softball team, plays as a shortstop with the softball team. A quick additional housekeeping here. The video recording of this webcast will be archived and available for you to download and review a week from today. You'll all get an email from us providing the link to the archived video next week. Today, we are going to kind of run through fairly quickly an overview of RainDance's products and technologies. I will do the next minute or so to give you that quick overview, and then I will turn it over to Jeff, who will go through the ThunderBolts Cancer Panel as well as the performance data before we open it up to the Q&A session. At RainDance, we are enabling groundbreaking research with innovative product portfolio of tools and applications to study cell-based and cell-free biomarkers for large population disease risk predisposition. Could be hereditary, could be carrier typing, could be constitutional diseases, as well as initial disease detection, focused cancer profiling and pathology, and finally, to the ability to monitor post-induction minimal residual diseases. In general, we offer a complete line of genomic products, systems, assays, and consumables that build on our digital droplet technology platform in order to help simplify complex genetics. Our core product portfolios are in 3 main areas. We have the Raindrop, the ThunderStorm, and the ThunderBolt. Our Raindrop system is our ultra-sensitive digital PCR system for research into early detection and monitoring of cancer, viruses, pathogens, and immune markers. Today, it is the most sensitive nucleic acid analysis platform in the market. Our ThunderStorm system is a high-throughput, fully automated NGS content enrichment solution that enables researchers to generate best-in-class data on large-scale disease panels while delivering the simplest and most affordable workflow for these very high-volume studies. And finally, what Jeff will be talking about today is ThunderBolts, our newest and latest NGS product. It is our next-generation cancer sequencing panel that enables researchers to profile a wide range of tumor samples, FFPE, plasma, tissue, etc., with as low as 10 nanograms starting input DNA in less than 2 days from sample to sequencing data, in a fairly streamlined workflow or at the lowest overall cost per sample in the industry. At this point, I will turn this over to Jeff to walk through the ThunderBolts Cancer Panel overview. Jeff?
Thank you, Omo. So what I'm going to cover today is an overview of the ThunderBolts Cancer Panel, as well as some experimental data generated in-house and with collaborators. This will be followed by a questions and answer session. So all the RainDance applications, Thunderstorm, ThunderBolts, and Raindrops, are based on the RainDance's core technology for very rapidly generating millions of tiny droplets in the 5 picoliter to 26 picoliter volume range to perform digital PCR. You start off with a sample which contains target molecules of interest, non-target background DNA, the PCR primers for specific target regions, and PCR regions. You then use microfluidic chips to divide the sample into millions of droplets, essentially isolating a single target per droplet, giving you truly digital PCR. These digital PCR droplets can then go on to be analyzed either by the RainDance Raindrop digital PCR platform, which basically reads out fluorescence per droplet. You can see an example up here where you have 4 different positive droplets, each with one single target molecule in. They have high fluorescence. These other droplets don't have targets in, so there's no fluorescence. It can also be read out by the next-gen sequencers, and that's what we'll be talking about today with the ThunderBolts application. The ThunderBolts Cancer Panel covers the mutational hotspots in 50 important onco genes, which are listed in this table here. The panel includes key driver mutations, tumor suppressor genes, and also drug-resistant markers. The panel is made up of 230 amplicons that are 150 base pairs to 200 base pairs long. The length of the amplicons was kept short so that the panel is capable of amplifying DNA that is highly fragmented and or modified, such as FFPE DNA and cell-free circulating tumor DNA. So I'll be showing you data in subsequent slides demonstrating excellent results when analyzing these types of difficult samples. The ThunderBolts Cancer Panel can handle a large range of sample types. In addition to the high quantity and quality DNA that's derived from blood, it can also handle samples of low quantities of DNA that are highly fragmented or modified. So for instance, breast tissue, fine needle aspirates. Now that's high quality DNA, but the amount of DNA you get is very limited, in the 10 to 20 or 200 nanogram range. Also, we can work with formula 6 paraffin embedded DNA or FFPE DNA. Now this DNA is very short and it's highly degraded and they're modified. And once again, the amount of available material is also limited, in that 10 to 100 nanogram range. We also can work with cell-free circulating tumor DNA. These are very short DNA fragments, and the DNA is very limited, only about 10 to 50 nanograms of DNA. As you also see, for FFPE and the cell-free circulating tumor DNA, I'd say less amplifiable. Often what we see is customers come to us with DNA that's OD'd or run on qubit. They say they have a certain amount of DNA, but when you actually look at the amplified amount of DNA, it can be much less. So as we'll see in upcoming slides, the panel can routinely handle these types of challenging DNA samples, even at low quantities down to as little as 10 nanograms. So as mentioned above, the Raindrop source can take a sample and divide it into millions of droplets. For the ThunderBolts application, we start out with 40 microliters, which contain the sample DNA, the ThunderBolts Cancer Panel primers, and the PCR reagents. And you go on to generate 8 million droplets. So you can see this. What this does is divide up the target molecules, and here we'll say KRAS, EGFR, TP3, and others. You just have a single molecule per droplet, giving you truly digital PCR. For instance, if you have 10 nanograms of DNA, which is about 3,000 genomic equivalents, and you have 230 target regions or amplicons, as we do in this panel, you end up with 690,000 positive reactions. That gets divided up into 8 million droplets. You end up with a 1 target per droplet ratio which gives you true digital PCR. Essentially, all the target molecules are in droplets by themselves. Other technologies that have a lower ability to develop or to generate compartments are not able to do this. Dividing the reactions into a very large number of very small droplet compartments has advantages. So one is there's no competition with other amplicons. Each droplet has only one target DNA molecule, so there isn't competition between the amplicons. Amplicons can have different PCR efficiencies due to things like length and GC content. So if you have two amplicons with different efficiencies in the same compartment competing for limited resources, usually the one with the highest efficiency will win out, generating more amplicons. In addition, because our amplicons have a very uniform volume, a very small volume, the amount of each reagent inside the droplet is also very uniform and limited. This results in PCR application in droplets plateauing at approximately the same level in each droplet. So both of these advantages for application in droplets results in there being a very uniform number of amplicon molecules generated in all the target regions. This leads to the generation of a very uniform number of sequencing reads, and thus uniform coverage of the target regions. This is important if you want to have confidence that you'll pick up variants through all your regions of interest. The high uniformity also allows the user to run more samples from MiSeq sequencing runs. Another advantage of the ThunderBolts Cancer Panel is that it features the RainDance RefSeq workflow. This allows the integration of the Illumina adapters and indexes during the PCR process. So in this case, you have a target region that is between 150 to 200 base pairs long. You have primers that are specific for that target region, shown by FFF and SSR, but you also have tails on these primers that have a partial sequence with Illumina adapter. After the primary PCR, which amplifies up the region of interest and adds the tail region, you do a secondary PCR application, which adds the remainder of the tails for the Illumina adapters, as well as indexes. This can then go directly onto the next-gen sequencing Illumina platform without having to do additional library preparation steps. This slide shows the workflow and the hands-on and total time for the ThunderBolts Cancer Panel for processing 8 samples. Your first step is just the generation of your primary PCR reaction. It takes about 30 minutes for hands-on and total time. You then load this on to a source, a raindrop source to generate the droplets. You just add the reactions to the chip, put the chip in the instrument, and hit go. It's about a 5-minute setup with about a 30-minute run. Here we have 10 minutes and 7 minutes because we have to do 2 runs for 8 samples on the source. You then just take those tubes off and directly put them into a thermocycler and do 55 cycles of PCR. You take those off the thermocycler, you add a reagent, vortex, and then centrifuge down the samples. That collapses the droplets and gives you an aqueous phase. That aqueous phase then does a very quick SPRI-select bead purification. That reaction is then goes on to the secondary PCR setup. Instead of a secondary PCR reaction, you do secondary PCR thermocycling. That incorporates the secondary, the Illumina adapters and the indexes. Then you do another bead, a SPRI-select bead purification. A quick quantification, we use Agilent that should give you something similar, or qPCR to do the quantification. The total time is about 2 hours and 45 minutes hands-on time and about 9.5 hours total time. Going through this whole process gives you a sample that is ready to go directly on the Illumina sequencer. Next, I'd like to show you some data generated both in-house and with collaborators using the ThunderBolts Cancer Panel on real samples. So this first slide contains data that demonstrates that the ThunderBolts Cancer Panel works well with low input amounts of DNA, both for cell line and FFPE samples. So DNA input amounts are ranged from 10 nanograms to 100 nanograms. It was processed with a ThunderBolts Cancer Panel and sequenced on the MiSeq. So this slide at the table we'll refer to as the standard sequencing metrics, which contain the pertinent information on the performance of the samples with the ThunderBolts Cancer Panel. So what you see on the left-hand side of the table is the type of DNA that we analyze. Cell line DNA with high-quality DNA, and then FFPE DNA. We next have the quantity of DNA, anywhere from 10, 50, and 100 nanograms, both for cell line and for FFPE DNA. What I've highlighted the boxes here are the lower amounts of DNA input for both sample types. We then have the sequencing reads, the total sequencing reads, followed by the map reads. So the map reads are the reads that map directly to your target region, nowhere outside the target region. Would you use that information to then determine what the percentage of map reads are? So you can see the percentage is very high, going from anywhere from 85% into the high 90% for percentage map reads. So the higher the percentage reads that map, the less capacity is needed per sample, which allows more samples to be loaded on the per MySeq run. And this is basically because you're not wasting sequencing capacity on off-target reads or garbage reads like primary diameters. To the right of that, you have the mean sequencing reads per amplicon. These are the actual numbers. But what we like to also do is we like to normalize to 2,500 reads. What that allows us to do is compare coverage between different runs where there might be a different number of samples per MySeq sequencing runs. The next column are the coverage that we get. What you see in the numbers is the percentage of amplicons that have that coverage or greater. You can see with our panel, 100% of the amplicons have 100x coverage at 2,500 mean reads. So the higher the coverage, the more confidence you have that you're going to be able to pick up a mutation regardless of what target region it's in, what base is being covered. On the very right is the 0.2x to the mean. This indicates the percentage of amplicons that have 0.2x to the mean reads or greater. This is one of our kind of uniformity measures. So the higher the percentage, the more uniform the sequencer reads between amplicons. The more uniform the sequencing reads, the more samples can be processed per run. Whether it's cell line DNA or FFPE DNA, ThunderBolts Cancer Panel deliver high coverage uniformity through all the target regions. So in another experiment, we created blends of DNA samples to test the ability to detect low percentage alleles with the ThunderBolts Cancer Panel. So we use 2 Coriell cell lines to generate the blends. So these 2 cell lines were sequenced by themselves with the ThunderBolts Cancer Panel to identify various SNVs between the 2 different cell types. The cell lines were then mixed together in blends of 90% to 10% and 98% to 2%. So for instance, if you have 2 cell lines, cell line 1 and cell line 2, in cell line 1 you have, at variant 1, you have homozygous A. At variant 2, you have homozygous C. Or in cell line number 2, for variant number 1, you have homozygous, the alternative allele, G. In variant 2 is heterozygous for the CG allele. If you mix cell line 1 at 90% and cell line 2 at 100%, what you get is a myelobulbar frequency for variant 1 for the G at 10%. For variant 2, for the G, you get a myelobulbar frequency of 5%. If you mix cell line 1 at 98% and cell line 2 at 2%, for variant 1, you get an allele frequency of 2% for G for variant 1 and 1% for variant 2 for G. So we were able to identify 4 variants at 10% and 2% allele frequencies and 12 variants at 5% and 1% allele frequencies. Each blend was run in quadruplicate and then sequenced on the MySeq. And this slide is a graph in which the expected allele frequency was measured with the, compared to the measured allele frequency. So as you can see, we're able to detect allele frequencies of 10%, 5%, 2%, and 1%. If you look at the correlation coefficient between the measured and the expected, the R-squared is really good. It's 0.9959, and you can also see the distribution is very tight at all these percentages. So in addition to this data on allele frequency detection, I'll be showing data in upcoming slides that demonstrates that the allele frequencies determined by the ThunderBolts Cancer Panel are not only consistent, but also correlate well with other orthogonal methods used to measure allele frequency. In this slide, the study that was run with the Robert Allen Lab at the University of Florida to compare variance detection results between the Appleseed Cancer Panel version 2 and the ThunderBolts Cancer Panel. So there were two samples that were analyzed in this study. The Appleseed work was done at the University of Florida, where they used the Appleseed Cancer Panel version 2 to process the samples and then run the PGM using the 316V2 chip. And then RainDance ran the ThunderBolts Cancer Panel on these same samples and then sequenced it on the biopsy. So you see there were 4 mutations found in sample 1 and 5 mutations found in sample 2. There's a good correlation between the mutants that were found and the allele percentages that were reported by both applications. What I want to point out is this number here in red. It was actually not detected with the automated pipeline or analysis pipeline. The reason being there was less than 25x reads. The pipeline rejects any mutation call or SNP call if anything that's less than 25x. Because our platform has excellent coverage, in this case we had 100% of the ample time at 200x coverage at 2500 mean read, we were able to pick up this mutation of the SNP using automated analysis pipeline. So because of our high consistent coverage and uniformity of ThunderBolts Cancer Panel, it gives researchers a high degree of confidence that they'll pick up a variant if it is present in the sample. So pancreatic cysts could be a precursor to pancreatic cancer. Current detection methods include radiological examination and cytopathological examination of the cyst fluid. So using these methods, there is a 10% false negative rate but also a 40% false positive rate where patients go through an unnecessary surgery. So we undertook a study with Andy Rem at the University of Michigan to determine if the ThunderBolts Cancer Panel could retrospectively identify samples with specific mutations that would indicate the presence of pancreatic cancer. So there was a limited amount of cystic fluid available, for the 5 patients, and there's only 10 microliters of pancreatic fluid that was used. It was analyzed by the ThunderBolts Cancer Panel for those 5 patients in this study. So you can see that in this table up here, which has the sequencing measures, that even though the samples have a limited amount of DNA, as little as 8.4 nanograms of DNA, once again you had excellent coverage, where 100% of the ample times had 100x coverage through all 5 samples, and except for this low sample that was 8.4 nanograms of input DNA, they all had 100% of the ample times with 200x coverage for 4 to 5 samples. Down the table below show the results, both the pathology results and the mutation analysis done by the ThunderBolts Cancer Panel. First of all, you notice that for the 2 negative patients, there were no mutations being picked up, showing that specificity is very high. But what you see in the positive samples is samples that were indicated to be positive by pathology. We picked up KRAS and GNAS mutations. There's been a lot of studies recently demonstrating and showing that mutations in KRAS and GNAS are very predictive to the progression onto pancreatic cancer. So in addition to these mutations that were found in these 3 samples, there are additional mutations that were found that are important in literature but are less lower prevalence. So these same 5 samples were analyzed with a RainDance digital PCR assay for KRAS G12D and with the current standard assay for KRAS G12D at a Sendot laboratory. So the top panels here show the output from our Raindrop digital PCR platform. On the left is a positive sample. We have 3 clusters. The first cluster down here on the lower left, those are the negative droplets. They don't have any target molecules in them at all. In the top left up here, there's a cluster, wild-type cluster. These are droplets that are positive for the wild-type allele. And then down here are the droplets in this cluster that are positive for the mutant allele, in this case G12D. The Raindrop digital PCR basically counts the droplets. In this case, so there's 26 mutant droplets for 74% wild-type droplets. On the right here is the negative sample, where now you only have 2 clusters. You have a negative cluster, and then you have a positive cluster for the wild-type. but there are no droplets in the immune cluster. So same samples were analyzed by digital PCR and compared to ThunderBolts Cancer Panel. What you see here is all the mutations were picked up by both technologies, and the allele frequencies once again correlate very well between the ThunderBolts Cancer Panel and the digital PCR RainDance system. But interestingly and surprisingly, the current assay call actually missed two samples, sample 1 and sample 3, which showing that at least in this set of samples, our sensitivity was much better than what's currently being used in the industry. So this demonstrates the sensitivity and precision of the ThunderBolts Cancer Panel, as well as the ability to generate orthogonal conformational data with two different applications run on the same instrument. So in a similar study carried out at the University of Paris, run a laboratory of Pierre Laurent-Puig, the ThunderBolts Cancer Panel was used to detect mutations in cell-free circulating tumor DNA and plasma, followed once again by confirmation by digital PCR. So there were 5 colon cancer samples and then 2 lung samples, and all these have been, primary tumors have been run with qPCR, which identified these mutations here. So one of the first things we did was to look at the input DNA either by qubit or by digital PCR. So qubit gives you the total amount of DNA that's present, what the digital PCR gives you is actually amplifiable DNA. So we took a digital PCR assay that was 200 base pairs long, which is the upper limit of our current panel, and then ran on the samples. So you can see the actual amount of amplifiable or usable DNA is much less than what's reported with qubit. It's down to as little as 0.76 nanograms of DNA. We went on to process these samples anyway, and as you can see, even with the small quantities of DNA, you still get very good uniformity. 93% to possibly 99%. You also got good coverage. Well, 100% amplifiers had coverage at 100x sequencing depth, 98.2 to 100% of the amplifiers had 5x coverage depth, and 93%, 99.1% it covers at 1,000x or greater. Once again, it shows that even with low quality DNA, you can get very good sequencing results. What you see shown here is the sequence results, digital PCR on plasma, and then ThunderBolts on plasma for those same mutations that were found in the primary tumor by qPCR. Once again, we picked up all the mutations, and the allele percentages were almost spot on for all these. This again demonstrates that we can obtain excellent sequence results with low input DNA from challenging samples such as plasma, and our ThunderBolts Cancer Panel to detect the same mutations in plasma that were identified in the primary tumor. And as with the pancreatic cyst samples, there was a good concordance for mutation allele frequencies detected with the 2 applications, the ThunderBolts Cancer Panel and the RainDance PCR instrument, demonstrated ability to get their affirming data from 2 different applications running the same instrument platform. So in addition to the data that I mentioned today, I also wanted to say that there's more validation data from other collaborators that are on the website if you're interested in exploring more. So in summary, the ThunderBolts Cancer Panel is a comprehensive cancer panel of important oncogenes. It covers hotspots in cancer, tumor suppressors, drug-resistant targets, driver mutations. There's a wide range of samples. There's biopsies, fine needle aspirates, FFPE DNA, cell-free circulating tumor DNA. It works for almost every sample we've ever tested. There's a low starting sample requirement, as little as 10 nanograms of input DNA. As you can see, that there are occasions that you go lower than that and still get good results. Very high uniformity coverage. So typically, 100% of the applicants have 100x coverage at 2,500 normalized mean read. This gives the user confidence that you can detect your mutations throughout your whole target region. There's also high sensitivity. We demonstrated in the slide earlier that the minor allele frequency of 1.5% can be detected with the ThunderBolts Cancer Panel. The workflow is very simple and very fast. It's 2 hours and 45 minutes of hands-on time to process 8 samples, and the whole turnaround time is also very fast. So going from processing the samples to getting your FAST2 files for analysis on the back end of the MySeq sequencer is less than 2 days. It's been streamlined to the Illumina sequencer. In this case, it uses the direct feed technology, which incorporates the Illumina adapters directly into the PCR product during the PCR amplification. And finally, there's a low cost per sample, as low as $100 all in. So going from processing the samples all the way through sequencing the samples, it can be as low as $100. So I want to thank you for your time today, and be more than happy to answer whatever questions you might have.
Thank you very much, Jeff. At this time, we will open the webcast to a Q&A. I want to start with a few questions we had already received during the registration process. So I would read out the questions and decide who's going to answer that. The first question is, what we got was, how many samples can be processed on Thunderbolt within the first 3 hours? I will have that to Jeff.
Yes, so we can do 8 samples with 3 hours or less.
Okay. The next question we got was, what do we define as an all-in cost? As Jeff mentioned, I would say that's almost. All-in cost is from sample preparation and purification all the way into sequencing data generated on the MySeq sequencer. That is the all-in cost. The next question we got was, what instruments are required to run the Thunderbolt assay? I'll pass that on to Jeff.
So it's very simple. You need the raindrop source for the generation of the droplet. Then you need a thermocycler for amplification, some methods for quantifying the DNA, whether it's Agilent or qPCR, and then the MySeq sequencer for the sequencing analysis, and that's it.
Great. Thanks, Jeff. The other question we got was, how many samples can you run on the standard single chip on the raindrop source for Thunderbolt? Jeff?
So there's 4 samples per chip with the ThunderBolts Cancer Panel.
Okay. So 4 samples per chip. And the other question we got was, can you address copy number variation analysis on the Thunderbolt assay?
Yeah, so we haven't done any copy number or CMV analysis on the for the raindrop for the ThunderBolts Cancer Panel right now. There is a system, a thunderstorm system, which is closely related, doing PCR and droplets for next generation sequence analysis. It's able to generate CMV data. Another thing we noticed when we run sample to sample with ThunderBolts Cancer Panel, the relative read between amplicons is very constant. That can theoretically be used to do CMV analysis. This is something that we have to validate going forward, and it'll be available sometime in the future.
Thanks, Jeff. Now we're going to go to live questions. For those who have submitted this, I'm just going to read those out to Jeff. He hasn't seen this question, so one of the questions was for FFPE samples, Jeff. If we detect a low frequency variant, how do we know it is not an artifact of FFPE?
Well, it might be an artifact of FFPE. All the cancer panels do is amplifying up the DNA. And if there's a modification in the DNA, it gets turned into another base during the PCR amplification, it'll come up as a true positive. So it's all about where you set your cutoffs or allele detection, 1, 2, 3, 4%, 5%, and that depends on the quality of the DNA. Now, there are bioinformatic tricks that you can do to try to identify real mutants versus false positives. But the ThunderBolts Cancer Panel will take the samples as they are. If there's a modification there, there's not much we can do about that.
Thanks, Jeff. The other question we had was, why do you need 2 channels per sample on the big channel chip?
There are 2 amplicon sets, set 1 and set 2 for the ThunderBolts Cancer Panel. That we use, at least in this case. Each one of them have about 115 amplicons in them.
Okay, thanks, Jeff. The other question was, how do you customize the panel content? And I'm going to take that one. At this time, the ThunderBolts Cancer Panel is not currently customizable. However, if you are interested in building your own custom cancer panel, feel free to contact RainDance and we can work with you on that particular request. The other question I got here is actually not Thunderbolt, but I will ask it anyway. If this system is so sensitive, how do you control for contamination on the thunderstorm?
On a thunderstorm? Well, it is highly sensitive, so basically you need to follow good PCR procedures. PCR room, the post-PCR room are very careful, change your gloves, change your pipettes, and so on. So because of the sensitivity is higher for a thunderstorm, especially if you get a thing other platforms like digital PCR, it just means you've got to be very, very careful.
The last question for Jeff, how easy is it to add UDG treatment for FFPE samples in the process?
So we haven't tested that out, and we need right now for Thunderbolts to use those specific buffers, and we haven't validated changing those buffers and what that might do as a result. So right now we don't support that.
All right, and the last question, I will take that on. The question is there any discount for batch or large orders by 100 samples, etc.? By any means, for this customer request, contact RainDance. We will process this information through our local reps, and we will get you a PO to cover whatever you want to run. New question coming in. The question is, all of the targets on the ThunderBolts Cancer Panel, do we provide the list? Absolutely. You will find this list in the ThunderBolts Cancer Panel product data sheet on our website. If you go down to the product area, you will find the ThunderBolts panel, and it has the entire 50 target genes on this panel on the website. You can download the product data sheet and get all of the information as well. And by any means, feel free to also access all of the presentations provided by all of the external researchers that have validated the ThunderBolts panel. This was presented at AACR back in April in San Diego, and there is a plethora of videos and recorded information there for you to kind of plow through. You'll get a lot more, as Jeff mentioned, a lot more information about the actual validation of this panel have been done beyond RainDance. So at this point, we are going to end the webinar, and thank you all so much for coming. I want to remind you that a link to the recorded video will be sent out to everybody next week. So look out for that video link. And again, thank you so much for joining us. Have a wonderful day, everybody. Bye.